Today we're going to spend some time looking at basic trigonometric, such a fun word to say, trigonometric identities. So our goal is that we're going to know and use basic theorems relating to the value of sine and cosine functions. So our first thing by way of introduction is just to remember where we derived this idea of cosine and sine, the definitions. Remember that the cosine is simply the x coordinate of the point on the unit circle, and the sine is just the y coordinate of that. So if you know the cosine of theta, then you can easily find the cosine of the opposite of theta. We could also find the sine of theta, and we can find much more, because everything is so interconnected that once we know one piece, all we have to do is play around a little bit to find the other stuff. Okay, so we can do so by using what's called trigonometric identities, which are equations that are true for all values of variables for which the expressions on each side are defined, as opposed to undefined, divide by 0. So if we recall, no matter where we place our theta, and we're going to focus right here just on the quadrant 1 to see where things derive from. Remember that when I have some theta that goes to here, then again, I have an x and a y point. And we already know that if this is my x, then this part right here represents the cosine. This distance is the cosine of theta. And the other component, this distance right here, represents the sine of theta. So looking at it as the triangle in a triangle. So if this here is my theta, then this length right here is the cosine of theta because it represents the x coordinate of that point that's over there. And then this one has to be the sine of theta. So now we have lengths. Instead of simply just a variable, we now have an actual number. Once we know what theta is, then I know how long this is, and I know how long this is. Of course, the Pythagorean theorem says a squared plus b squared is equal to c squared, which means, in this case, the cosine of theta squared plus the sine of theta squared is equal to what? How long is this right here?
1.
It's the tangent, but since it's my unit circle, it's a 1. So notice what we just found out. And the way that we write it, instead of getting confusing with the parentheses and the square, we just like to put the square next to the cosine, but it means the same thing. The square of theta, cosine of theta squared, is another way of saying is cosine square theta. So those are equivalent statements. So notice it's simply a squared plus b squared equals c squared, and c squared is 1. So this is called the Pythagorean Identity Theorem. Okay, so let's look at page 2 and look at an example. If the cosine of theta is 3 over 5, or 3/5, what's going to be the sine of theta? Well, we're going to start off with the Pythagorean identity. Now, you don't have to write this every time. Just for now, I'm writing it just so that you see what's happening. I already know what the cosine of theta is. It's 3/5, so all I'm going to do is substitute it in there. So notice the 3/5 has to be squared, plus the sine squared of theta is 1. Just to simplify here, this part here becomes 9 over 25, plus the sine squared of theta is 1. Now I'm going to subtract from both sides to get 16 over 25. 1 minus 9 over 25. And of course, when we take the square root, looking back to your Algebra 2 days, beep, 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 don't forget that you have a plus or a minus. Don't forget you have a plus or minus mathematically. So, carrying this over, the sine of theta is equal to plus or minus 4/5. So check your answer here for example 2. And tomorrow we're going to walk through other theorems besides the Pythagorean identity. So let's walk through and see how you did. If I take any theta, and so let's randomly choose. Some of you probably chose something like 50. So, and it could be anything. But if you chose 50 degrees, then this would be approximately where it lives. So move that out of the way. Now, if we wanted to use our calculator to find out what cosine is or what sine is, or we could just use our approximations right there to find those. Notice that P2 is, so this one is P1. Now P2 is just the negative of theta. So instead of going positive 50 degrees this way, we're going to go negative 50 degrees. So in that direction. So it's going to place us right here. So here's P2. But notice what doesn't happen. You don't even need to know the numbers to see it. That the x value stays the same. So since the x value stays the same, we can actually answer this question. Taking the opposite of theta does nothing to cosine of theta. It keeps it the same. However, notice that my y value, my sine, is positive here, but then down here it's the same, just reflected, and it's the negative. So, but takes the opposite or oppositifies sine of theta. Next is P3, so we're going to go 180 degrees. If you didn't know that, 180 degrees would hang out over there. It's just a reflection that way. Or we look at it as 180 degrees this way relative to P1. Okay, now we're going to see where that is and notice what happens. Here is my new x value compared to that one. And here's my new y value compared to that one up there. So what does 180 degrees do to both of those? Good, it oppositifies things. So this one here is now going to be negative and now going to be negative. So what's the conjecture we can make? Something like this is that if we add 180 degrees or if we go halfway around or something like that, it takes the opposite of both the sine and the cosine. And so we might say something like this. All right, which brings us to, we're going to look at 4 theorems today, 4 different identities. Yesterday we looked at the Pythagorean Theorem identity, or the Pythagorean Identity. So now we're going to add to that opposites, half-turn, supplements, and lastly the Complements Theorem. All of these are intertwined. You will be confused on this, so making a decent summary table is going to be helpful. So first off here, opposites theorem. For every theta, if you take the opposite of theta, cosine remains the same. If you take the opposite, then the sine becomes opposite. So it's the opposite of sine theta. And as you know, since tangent is derived from cosine and sine right here, notice I have a negative over a positive. So that means tangent will also be negative. So going in the opposite direction does not change cosine, but it does take the opposite of the other two. Well, next up, half turn of cosine. We know that it says take the opposite of cosine. This last one over here is just to write it in terms of radians. So pi plus theta instead. So I'm going to say that over here. These are radians. And these are degrees right there. So we already mentioned the other one, that when you half turn your theta, you do take the opposite of sine. If sine is originally negative, sine then becomes positive. And of course, that's simply just saying pi plus theta. Half a rotation. And of course, we can derive tangent just by looking up at these ones. Negative, this negative divided by this negative is positive. So that means taking a half turn for tangent doesn't make a change. Tangent remains the same. And now supplements. Supplements. The supplement of a cosine. So when you supplement it, you do take the opposite. In other words, it takes it to the other quadrant, like it reflects it across. Again, putting that in radians is just saying pi minus theta. However, if you take the supplement for sine, it makes no change because it keeps it on the same level, keeps it above the x-axis or below the x-axis. And again, that is pi minus theta in terms of radians. And lastly, we can see the derivation here for tangent. Here, now I have a positive divided by a negative. So supplementing the theta means I will take the opposite for tangent. So now let's look at an example of an application here. So given that the sine of 10 degrees is approximately 0.1736, if we're going to find the other value, or a value of x other than 10 degrees, that's between 0 and 360, for which sine is the same, which is also that. Well, all we have to do is go up here and figure out what change do I make, and sine remains the same. So if I take the opposite, sine is opposite here. If I add 180, sine is opposite here. But if I take the supplement, sine stays the same. So the answer to this is to supplement that. So supplement 10 degrees, which is 180 minus 10. So the answer is 170 degrees. The test for it is just to plug that into your calculator. Our last identity for this section, and there are dozens of other identities. Fortunately, we're not going to get that deep into them, is the Complements Theorem. And the Complements Theorem is almost the same, except it would be wise to look at a phase shift. All right, so what we discovered by that graph was this, that when we complement theta, it shifts and becomes sine. And when we complement sine, it becomes cosine. And that in radians, again, would be cosine of pi over 2 minus theta. And this one would be sine of pi over 2 minus theta. And I got overzealous here with my copying and pasting, so that one's there. All right, so I took a moment here to see how things change. I don't know if color coordinating would help or whatever. So notice that in certain instances, opposites happen in these instances. So taking the opposite does not guarantee that things will opposite change. So taking the opposite here does not change here, but does here. Rotating changes these two, but not this one. Supplementing changes these two, but not this one. And then lastly, complementing switches the two. So let's use this chart to help us out with this problem here. So we are given the sine of 30 is 1/2, and that's it. And our job is to find the cosine of 60, the cosine of 30, the sine of 150, the cosine of 210, and the sine of negative 30. All right, so the key is to recognize what is happening here. So notice that 60 degrees relative to 30 is a complement. Okay? So if we complement 30, so notice what happens. If we complement it, the sine now becomes the cosine. So, in other words, the cosine of the complement is the same as the sine of the original. So that being the case, this is 1/2. So what we're deriving here is with no calculator, without the assistance of the tech. Now, cosine of 30, how do I get to the cosine of 30? This one takes a little bit more work. because we are going to use the Pythagorean identity. So that being said, we know the sine squared, the cosine squared, so I'll call it a squared, plus my sine squared is equal to 1. So continuing on to get this, so a squared is equal to 3/4, and then a is equal to plus or minus radical 3/2. Obviously, we have two results right there. So the cosine of 30 degrees is equal to radical 3/2, using the Pythagorean identity. Looking at the next one, the key is to look at the 150. How does the 150 relate to the 30? Oh, there's supplements. So let me go down to the chart and see what happens. If I supplement it, how does it change my sign? It doesn't. It doesn't change my sign. So the sign of 150 is also equal to 1/2. And this is the supplements ID. Next, the cosine of 210. Well, that gets a little bit more complicated because how does it relate to the 30? To this 30? Well, to 30, it's 30 plus 110, or excuse me, 180, so that's a half turn. But notice I'm dealing with the cosine, not the sine. So I need to look at the b there. Because the b is the half turn, so it's the half turn of the answer of this one. So remember the half turn, how does it affect cosine? It just says take the opposite. Take the opposite. So for cosine. So in this case, taking the opposite of plus or minus is still plus or minus. So the answer is here. So this is the half turn ID. And the answer is still going to be the same as part B. You could say minus plus instead of plus minus, but ends up being the same. And the last one says instead of taking sine of 30, we take the opposite there.